welcome to our next section on electric current, resistance, and Ohm's law. In this section, we're going to be focusing on electric power. Now, hopefully you remember that power was defined as energy per time. And what we want to do here is rewrite our formula for power in terms of the quantities we have for electricity. So I'm going to remind you that voltage was by definition electric potential energy divided by a factor of charge, and current is charge per time. So if I take voltage and multiply by current, I divide by charge, I multiply by charge, and I'm left with energy per time. So I can write that power equals current times voltage. The other thing that I have is I have Ohm's law, which tells me V equals IR. If I plug in Ohm's law for voltage, that gives me an alternate form for electric power in that current times resistance, or in other words, I squared R. Or I can take and rearrange Ohm's law so that current equals voltage divided by resistance and plug that in. So now I have voltage divided by resistance times voltage, and that gives me my third form, V squared over R. So there are three ways I can write my formula for electric power, and I'll put them all up here nicely at the top for you. Power is current times voltage. It equals current squared times resistance, or it equals voltage squared divided by resistance. And now you look at that and you go, but which do I use? Which formula is correct? If you do it properly, they will all give you the same answer if you do things properly. What I would advise is taking and looking at what do you know, what don't you know, and then choosing the correct version based on the information you have. So let me give you a bit of an example here. We have two formulas here. P equals V squared over R. And this implies that the power dissipated by a resistor decreases as resistance increases. So if I divide by a bigger number, I'm going to get a smaller number. So power will go down as resistance goes up. I'll even put that in with little arrows. If I look at the other version, power equals current squared times resistance. That says that the power dissipated by a resistor increases as the resistance increases. So power goes up as resistance goes up. And this looks very contradictory. But I've already said they're all true and they can all give you the same answer. So which one of these is correct? The key to this is thinking about what is constant, what isn't constant. So I'm going to go with an example that is typical for electric circuits. And the thing that is constant is the voltage. Okay. If I think about taking and plugging my lamp into a wall socket, that wall socket is going to supply 110 volts to my lamp, assuming it's a standard outlet here. If I plug in my computer, it's going to supply 110 volts to my computer, or to my toaster, or my blender, or anything that doesn't require a specialty plug like a dryer or an electric stove or something like that. Voltage is constant. Okay, if voltage is constant, then certainly if I change the resistance, the power will change. If voltage is constant, then changing the resistance also changes the current by V equals IR. So with V equals IR, if the resistance increases, then the current has to decrease in order to keep the voltage the same. And now, yes, it's true that if the resistance goes up, something will change, but not in the way we think, because there's another piece that's also changing. Current isn't constant in that second equation. It will go down as resistance goes up, for example. I don't know how clear I was on this. Feel free to ask me, and I will try again to clarify it. Let's think about power in your house or in your dorm. If you get a power bill or have looked at your parents' power bill, or Google power bill, what you'll see is that you are charged by the kilowatt hour, kWh. Kilowatt hour. Okay. What is this exactly, though? Well, watt or kilowatt, that's just your Greek, your metric prefix there. Watt is the unit of power. Okay. Hour is a unit of time. So if I think about this, kilowatt hour is units of power multiplied by time. And now we're going to go back to our definition. Power equals energy divided by time. So energy equals power multiplied by time. So kilowatt hour, what I'm charged for, I'm not charged for the power I used. I'm charged for my energy usage. Charged for my energy usage. Which actually makes a bit more sense here. So now let's think about power and energy usage and these sorts of things, and consider an electric stove. Okay. Electric stoves draw between 2,000 and 5,000 watts. So that's a measure of the power. Okay, why does it change? Well, sometimes we turn our ovens on to 350 and sometimes we turn them on to 425. So when you need more heating, you need more energy here. Okay. Typically they're plugged into a 220 volt source. So how much current do they draw? Well, again, it depends, but we can do both ends. So P equals IV, which means current equals power divided by voltage. Now, why did I choose this version of the formula? Because that's what I had the information for. I knew power, I knew voltage, and I wanted to know current. So why would I bring resistance into this? Okay, so two options. One option is 2,000 watts divided by 220 volts, and that equals a current draw of 9.1 amps. My other option is 5,000 watts divided by 220 volts, and that is 22.7 amps. Okay, this large current, this one right here, is why your oven, besides the fact that it's on a 220 voltage source circuit, has to be on its own circuit breaker, because that is a very large current. Okay, the next question. If electricity costs 12 cents per kilowatt hour, how much will it cost to operate your stove for 3 hours? Okay. For that, I'm going to go to the next slide, and I'm going to remember that power equals energy per time. or energy equals power multiplied by time. Now you're wondering, well, why did she go here? Because the units of my cost were per kilowatt hour. And as we just discussed, kilowatt hours are units of energy. So I need to get to energy. I have two possible energies, one for 2,000 watts being operated for 3 hours, which is, I don't need to do a unit conversion there. 2,000 watts for 3 hours is 6,000 watt hours, or 6 kilowatt hours, or it could equal 5,000 watts multiplied by 3 hours, which is 15,000 watt hours, or 15 kilowatt hours. I can now find the total cost, and that's going to equal the cost per kilowatt hour multiplied by the number of kilowatt hours, or multiplied by our energies. So in the first case, I have 12 cents per, that's a K, kilowatt hour multiplied by 6 kilowatt hours, and that works out to be a whopping 72 cents. In my second case, I have 12 cents per kilowatt hour multiplied by 15 kilowatt hours, and that is $1.80. This concludes this section. In the next section, we are going to look briefly at AC circuits, which are actually what occurs in our houses.